Okay, why don't we start? So, a couple of logistic questions. So, the first assignment is due today, I believe. So make sure that you are submitting your first assignment. As I mentioned before, you have 5 penalty days for the rest of the assignments, right? So you can use it however you want to use it. I know a lot of people will try to use it for this assignment, but just to tell you that, the second assignment is not going to be easier, and the third assignment is not going to be easier. So if you're using your late day for this assignment, you have to think very carefully how you're going to be doing your second and third assignments. The midterm is going to be on October 9th, which is Monday. We'll send out details of where it's going to be. So I guess there's going to be 2 sections, this section and the online section, all writing it together. So we'll come back to you on this. Any specific questions? Projects, also, you should be thinking about your projects. I'll set up the date sometimes towards the end of October. You should be producing a 1-page project proposal, and you should really start thinking about the project because it's a substantial part of your grade for this course. Okay, so today what we're going to do is we're going to continue looking at convolutional neural networks, but today's lecture is going to be less of a technical lecture, more of an application lecture. Okay, just to show you some of the recent advances in convolutional nets. Next class on Wednesday, we're going to start diving into graphical models so that we have a better understanding of what it is. And we're going to start looking at restricted Bose machines, variational autoencoders. So we're going to start looking at more advanced state-of-the-art models, particularly for unsupervised learning. Okay? Okay, so just a little bit of a disclaimer. If you're interested in convolutional neural networks, there is a whole bunch of different tutorials you should look. There's an excellent tutorial by Rob Fergus on convolutional nets, as well as some slides from Marco Aurelio Ranzato from CVPR tutorial. So there is a lot of material online as well, if you are interested. Okay, so one of the things that we're going to be looking at is invariances that are built into convolutional networks. So remember when we were talking about pooling operations, like a max pooling operation, that basically introduces small translations, right? Convolutions and max pooling. So these models can be invariant with respect to small translations in the input space, which makes these models generalize much better. As well as sometimes these models can handle small contrast or illumination effects. And this is due to local contrast normalization, right? Sometimes when you do contrast normalization, as we've talked in the last class, you can be invariant to that as well. But in particular, it's not invariant to other variations, such as rotations or scale changes, right? So if your object is rotated, nothing is built in the convolutional network that can take this into account, right? And that's actually one of the areas of research where people are trying to figure out how can we incorporate, structure into the convolutional net so that they can be rotation invariant, right? So if I take a particular object, I rotate it, 45 degrees, the model will not be able to recognize it, right? In particular, if you haven't trained it, if it hasn't seen these rotated objects at the training time. Scales, the same problem. Most of the time, you're detecting things at a smaller scale, and you see like detecting cats in smaller scales, and you see a large cat, a big cat in the image. The model is not. It's most likely the model will fail, right? So these are things to watch out for. But it's very easy to generate artificial data with such transformations, and that's actually one of the most commonly used technique to make these models be more robust, which is take the data, generate a whole bunch of artificial data by rotating, translating, flipping objects. In particular for, in computer vision, what typically happens if you try to recognize a particular object, if you flip it, it's going to be the same object unless, symmetry matters. Like if you have a cat, you flip the image from, left to right, it's still going to be a cat. And that turns out to be a very good thing to give to the convolutional net so that it can deal with it. So you could use such data as an additional training data. And neural networks can potentially learn, rotation invariance or scale invariance for these transformations, right? If you can generate artificial data. It's the cheapest way to do it because you don't have to collect the data if you can do it. So let's look at some examples. What's typically is done. Here's the image. One of the things that typically happens is that people crop the image, right? And then this is a cropped way, and this is what you kind of like pass it to the neural network, right? You can crop it at different positions as well. That substantially helps generalize model performance. In fact, the winning competitions that you see on ImageNet, a lot of different computer vision tasks, this is what commonly is done. You're cropping at different locations. You can also do translation. As you can see, the cropping, you're translating it. You can do rotation. Right now, you have to be careful exactly how you do rotations. It's a little bit tricky because if you rotate it and then you undo the rotation, you come to the original image size. The image might look funny. Exactly how you do it, using bicubic interpolation or whatever it is you're using, can have an influence, right? Whenever it says undo here, that basically means that the resolution of this image is exactly the same as the input image, right? So the network always sees images of the same size. In this case, I think it's 250 by 250. Scaling, it's the same. You can zoom in on at least part of the object, crop it, and then zoom out, right? So now you can see you have all of these different sunflowers that you give to the model, and you basically say it's the same class, same sunflower class. Yeah, there's a question?
So let's just say you had an image like this one, and then you want to rotate it. Would it ever make sense to add white space instead of cropping, or would you generally want to crop?
Generally, you'd probably, you can add white spaces, but what happens is that you have to give it, this is a rotated sunflower. I mean, it doesn't seem like it's rotated, but this is a rotated sunflower, right? So when you want to make sure whatever you give to the input here, you want to make sure that this is something it's likely you will see at the test time, right? So that's why sometimes you crop it, and that's the best way to do it, as opposed to just, filling in the white spaces, right? Yeah.
Is it the best way to carry this rotation, these additional examples? Is there any other structural neural network like
No, there's been a lot of work. People are trying to use sort of like group theory and rotation group theory to enforce that structure into these models. But so far, nothing has been very successful. There isn't a single method that can do it. The best performing systems today are just using these things. It's cheap. You can do it on the fly. You don't need to have labels because you know what the label of the original input is. You're just generating a whole bunch of different examples. You just have to be careful how you're generating them, right? Because if you generate something that's not realistic, then you can hurt the performance of the model. Yeah. Maybe just one last question.
Can we add a noise for the original image so that the neural network can recognize the noisy data?
Yeah, you can add the noise. There is a lot of work later on. We're going to look at this class at denoising autoencoders or various denoising models. You can try to add some noise. You can try to add occlusions and try to make your model be robust. But so far, the best systems right now are kind of just using these techniques: cropping, flipping, rotating, scaling it, the data sets. Right. OK, so let's look at one particular example, which is known as elastic distortions. And this was done a decade ago, but it's useful for character recognition. And perhaps it could be useful in computer vision techniques as well. So what we can do is we can make changes to the input by applying a distortion field to the image. And the idea is that the distortion field would specify where to displace each pixel. So for example, here's the input. This is your distortion, random distortion, right? So for every single pixel location, you just randomly draw a vector where you want to displace this pixel, right? If you do that, you're going to get something like this. right? Just a second. And so if you actually have a smooth random distortion, so you're smoothing it, and here you're basically saying, what is basically saying you don't want to have too much randomness. You have this. And here is another example of smooth distortion, which basically means that nearby pixels should be moving in the same direction, right? And there are ways of doing it. So now you can see that this particular image transforms into this other image just by displacing pixels, right? Which is kind of cool. Yes?
How did you determine that set of space range on the pixels?
Typically, you would just play with it and figure out how much displacement you want to do. So here's an example of again, let me just see. So here's an example again of taking image 6. You can see these distortions are fairly smooth, and so you can have a specific distortion of that particular image. And I believe that the neural nets with elastic distortions were basically state-of-the-art models for doing image recognition. So if you take convolutional nets, you add elastic distortions, or people even were looking at support vector machines and adding elastic distortion without incorporating all the translation convolutional structure, you could get quite strong results. Like errors were below 1% accuracy for recognizing these 10 different digits. So this is one example. I believe there's been some work in computer vision where people are also trying to figure out what the distortion should be. Take an image, distort it, to have an additional examples. These are just some examples of what you can do. You can recognize digits. Obviously, you can recognize street housing numbers. You can recognize traffic signs. Here's an example of pedestrian detection system, and you can see that it's actually working really well. Like if you look at this crowd, you can pick up a lot of pedestrians in this crowd, or somebody riding a bicycle. So these are detection systems that are predicting bounding boxes. Here is another case of object detection, which is kind of interesting. So here, you're basically proposing a single box. But the model could also propose multiple boxes and multiple boxes. And what you're seeing here is the way that people currently deal with scale. There are better techniques right now, but before, to deal with multiple scales, you just take the same image and you upscale it, right? By applying, and you're still applying the same model. So if you have larger objects, you can still detect them. Right? It's computationally more intensive, but nonetheless. If you're interested in kind of looking at some of these examples, some of these detection examples, here's some literature for you to look at. Now, let's look at the ImageNet data set. This was created back in 2009. You have about 1.2 million images. You have about 1,000 classes. And here you're looking at examples of a hammer, right? So you can see the diversity of all the different examples of a hammer. Like this is a hammer, right? It's pretty interesting. It looks like a dagger. But hammer, like all of these different objects. You can see it's very, very diverse. Recognizing hammers, it's pretty challenging by just seeing that, right? You have to sort of understand something about how hammers look like, different views, different orientations, different backgrounds, and so forth. So it's quite a challenging data set. And as I mentioned before, back in 2012, there's a paper published on ImageNet that basically won the ImageNet competition by using this deep convolutional neural net. And a lot of people were surprised because if you look at accuracies, you can predict that this is, leopard, and this is Madagascar cat, even though it's predicting a squirrel monkey. So it was basically the system that could do way better than whatever people could do before by, a large fraction. So that surprised a lot of people. Because before 2012, these neural nets and convolutional neural nets were always kind of like the second best. The first best was always compute a whole bunch of features using SIFT, typically people would compute 300,000 different features and then do clustering and then create these gigantic features, push them through support vector machines and then do classification. This is These were state-of-the-art models, and it was always very difficult to construct them because there's so many choices involved. How do you extract SIF features? How many? How do you do clustering? There's a bag of visual words. How do you apply SVMs? There's a lot of different pieces that went together for these models. But this system kind of surprised a lot of people in 2012. A lot of people actually thought that something was wrong with this data set. And it's like, it can be right. But later on, just basically turned out that these models work surprisingly well. Now, let's look at the architecture. How can we select the right architecture? And there is a joke right now that the manual tuning of features is now replaced with a manual tuning of architectures. Right? So if you look at the vision and speech field, before 2012, people were tweaking features. Do I use Hog? Do I use SIFT? How do I construct bag of visual features and so forth? Now everybody's tuning architectures. How many layers? What the nonlinearities? What are hyperparameters? I guess from your second homework, hopefully you will see that it's not a clear solution. Right? Different hyperparameters, different architectures, different regularizations, and so forth can lead to different performance. Right? So it's not an easy thing to do. Now you have to care about depth, width, parameter count. So what can we do? So, and there are lots of different hyperparameters, right? Number of layers, number of feature maps. One common technique people are using cross-validation, right? So use your validation set to pick your hyperparameters. What are the learning rate? What's the size? And so forth. Typically, one strategy is to use grid search, which is to say I have 10 hyperparameters, I'm going to just do grid search, just try a whole bunch of different hyperparameters. Right? Obviously, that requires a lot of compute. So typically, you'd run 800 jobs, you try training different models and such to come up with the best setting of the hyperparameters. And then there are smarter strategies. There is something called random search, which is based on decision trees. There's been some work on that. Also using Bayesian optimization, where you build a Gaussian process on top of your hyperparameters and try to figure out which hyperparameters you should be choosing next. The downside of Bayesian optimization is a sequential procedure, and so a lot of people just stick with the grid search. Right? Just try a whole bunch of different hyperparameters and then come up with the best setting. Yes?
When you do this grid search, do you do a combination of parameters or do you have one parameter less than the other one?
Yeah, so you can think of it, if you have like 5 parameters, you have a 5-dimensional cube. Right? So, and obviously, based on your problem that you're trying to solve, you will kind of figure out approximately what are the right hyperparameters for you to look at. So you come with some prior knowledge. Like you wouldn't try a learning rate of 1,000. It just doesn't make any sense, right? Or you wouldn't try like a dropout, some ridiculous dropout, right? You'd start with like 0.5 and try to test 0.4, 0.6. So there is a range of hyperparameters that you think is reasonable, and so you can do that. Okay, so let's look at the model called AlexNet, which is again was developed by Alex Krzyzewski in 2012. And this particular model that was beating state of the art at that point, which is actually very funny, because Alex he was a student at Toronto and he built this model, won the competition, was giving a talk at a CVPR workshop on this problem, and basically said something like, yeah, I just had a computer with a couple of GPUs in my bedroom, and it kind of worked, which kind of upset a lot of computer vision people because, it's like you work your entire life, and then some kid in the bedroom just built something that works so much better. But nonetheless, so this is trained on ImageNet. You could get 18% accuracy. Top 5 error, right? So top 5 error basically means that you pick the top 5 predictions, and if one of them hits the correct class, you consider it to be correct. And this is done primarily because there's so much noise in the data. It could be multiple objects. As long as you hit one of them correctly, you consider it to be correct. The best performing hand-engineered system at that time was 27 or 28%. And that was done by large teams, computer vision teams from well-known universities who were competing on this particular data set, right? So it dropped from 27 to 18%. And if you do sort of ensemble of these methods, you could go down to 16%. So again, it was a huge gap in accuracy. But now, so let's look at the architecture itself. It's an input image. You basically have convolutional plus pooling, convolutional plus pooling, convolutional plus pooling, fully connected softmax output. Okay? Now, this particular model had about 60 million parameters in it, right? So if you take the top layer, the fully connected layer, and you just drop it and just train this model, so you drop about 16 million parameters, it only drops 1.1% on performance. So the performance suffers, but not by that much, even though you're dropping 16 million parameters, right? Now, if you drop layers 3, 4, 6, and 7, so it's like conv, fully connected softmax, much shallower network, so you drop about 50 million parameters. You have about 33.5% drop in performance. Right? So that was basically saying something about maybe the depth of the network somehow matters. Right? So number of convolutional layers that you're injecting in this particular model actually made a big difference because the drop in performance is substantial. So then people started looking at these models and started figuring out, okay, can we go beyond these models? And then in 2014, Google had introduced this model, GoogleNet, which is again has become one of the baseline models for image recognition. You have 24 layers that we're using so-called inception modules. Inception modules really, what they were doing is they were combining different convolutions. So, one feature map would have 3x3 convolution, the other feature map would have 5x5, the other one would have 10x10, and all of them would be coming to the same hidden unit. So instead of having convolutions, which is always 5x5, they were combining it at multiple scales. And that was, that was helping them. The other trick that they've done, which seemed to help, is to have these softmax output layers. So in other words, you have a label here, and when you do backpropagation, this label would backpropagate through here. And you have a label here, and it would backpropagate here. You have a label here, and it would backpropagate through here. So this was done primarily because of the vanishing gradient problem. If you have only labels here, backwards through this entire model was very difficult, right? So what they've done, which is what, again, was done a lot of times by a number of research papers over the last decade, is to inject these, these additional kind of prediction layers. So you want to predict correctly here, you want to predict correctly here, you want to predict correctly there. And it was done primarily to force the labels to propagate, fix a little bit of vanishing gradient problem. And so what's the inception layer? Well, you have multiple filters, multiple filter scales at each layer. So, you can look at 5x5, 3x3, 1x1. So here, if you have a previous layer, you'd use 1x1 convolution, you'd use 1x1 convolution, 3, and so forth, 5x5, and everything would come together. Right? So they found it was helping them to mix together convolutions at different scales. Right? So the width of the inception modules was ranging from 256 layers. So at early layers, you'd actually have 256 filters. So you have 256 feature maps, which is a lot. Right? And each feature map is some representation of the image. So it's almost like you have 25 times whatever the size of the image. Right? So it's kind of eating up a lot of memory. Well, the other thing that they've shown is that you can actually remove fully connected layers on top completely. So everything is convolutional, which is interesting because fully connected layers is what's eating a lot of parameters. So if you remove the fully connected layer, then the number of parameters, I think the number of parameters in this model was like 1 million. So you go from 60 million of the original AlexNet to about 1 million, or maybe a couple of millions parameters in this model. So it's a huge reduction in the tunable parameters, right? Oh, it can be reduced to 5 million. So they only had 5 million. They go from 60 million to 5 million parameters. So it's a deeper network. You get about 6.7% top 5 validation error, was about 7% on a test set, right? So it's a drastic reduction in accuracy. You have a deeper model, and you remove fully connected layer. The other interesting thing about removing fully connected layers, so what they were doing is they were just basically averaging everything at the top. So at the top, you have these different layers that are coming up, and what you do is you just average them, right? Once you average them, you have a fixed representation, and you pass it through the softmax classifier. And the argument here was that, well, the size of the input doesn't actually matter. So if you give it 250 by 250, or you give it 250 by 300, or 300 by 280, it doesn't really matter, because these are all convolutional features. At the very top layer, you'll just average all the outputs. So it was invariant with respect to the size of the input. So you could deal with images of different sizes, which is kind of interesting. Yeah. Yes?
Google there has also different insertion models, like the version 1, version 2, version 3. Could you tell us the difference between?
I have no idea. There's version 1, there's version 2, there's version 3. All of it is just iterating on these different architectures.
Well, I do know the version 3 has like one by one convolutions at the end after the 5 which makes it faster to run the training. But I was just wondering what the differences were as opposed to version 1 and 3.
Yeah, my understanding is that a lot of these models, they just go through iterations by either making them faster or introducing, these by-one convolutions, but the overall architectures basically remain the same, right? The architecture is that you have these inception modules, you have these layers that are coming in, and so forth. And then you just iterate on different architectures, because in some cases you can make it faster, you can make it more accurate, and so at this point, I think a lot of it is just the architecture search. There is nothing particularly novel, between V1, V2, V3. All of it is just tuning your architecture. And then, I guess in 2016, there was another paper. Oh, I should also point out that I haven't put the slides, but at about the same time, when GoogleNet came online in 2013, there was also another model coming from Oxford that was called VGG network. It's also one of the baseline image recognition models. And they were able to achieve about the same performance, or in some cases even better performance than the original Google's model. And it was done by one grad student, which is remarkable. And the trick there was to basically use, as I mentioned before, I think in the previous classes, is to use 3x3 convolutions. So you take the whole image and you just do 3x3 convolutions, and you build however many 20, 25 layers of just 3x3 convolutions. Right? Nothing interesting, nothing spectacular. 3x3 convolutions, you do it 25 times, you get state-of-the-art accuracy. All right? So, and he had to do some work because it was such a big model doing 3x3 convolutions that they had to split it across a couple of GPUs. So you have to do model parallelization because it wouldn't fit on a single GPU. So there are a few technical coding skills that you had to do, but that again now it's one of the baseline models. So typically when people use image recognition, you either use GoogleNet, the latest version, or use VGG network. It's commonly used network, right? But this tells you something about also the architecture. It's not clear what architecture is right, what architecture is wrong, right? So there aren't a lot of intuitions as to what your architecture should be for a specific problem. Now, in 2016, there was another paper that I want to mention. It's called Residual Networks. And that basically was coming out, I believe, of Microsoft Asia. And they were basically able to achieve, again, state-of-the-art and would beat Google and VGG network. And so this model is right now kind of the baseline model that everyone is using. So let me show you one interesting thing about what they've discovered. So here's a training error plots versus iteration, and there is a test error plots versus iteration. So if you're building a 20-layer model, right, the training error goes down, stays here. If you look at the 20-layer model, the test error goes down and stays here. Okay? Now, if I'm going to build a 56-layer model, look what's happening to the training error. The training error is higher than the training error for the 20-layer model. What does this mean?
Deeper into the world.
It's too deep, but you know, what does this set tell you on this training set? What's the problem here? It's not overfitting. It's not even overfitting. Overfitting would be, your training error would be 0. Underfitting. So this is a classical problem of optimization. Because this model has more parameters than this model. So it has to fit the training data better, right? If I have a larger, bigger model with more capacity and I apply it in the same training set, it should be better. This is basically pointing to you that we don't have good optimization techniques to train these models. Because, you know, the gradient gets vanished after 56 layers, nothing gets propagated, so you can't optimize it, right? We're not even looking at the tester, we're just looking at the training error, right? It's a pure optimization problem. We can't really optimize these models. And if you look at the test error is also worse, right? So this is not a problem of overfitting. This is a problem of underfitting. You can't really fit this model. So its test error is even higher than a 20-layer model, right? So if you try building these very deep models, it's just not going to work because you can't optimize them. So that's why, as I mentioned, I think in the last class, a couple of classes before, in neural nets, optimization is one of the big areas of research. People are trying to figure out, you know, how do I do optimization? Maybe if you use second-order methods, or maybe if you use something better, you could optimize these models better. But what residual networks folks did is they basically introduced pass-through into each layer. And basically, they've introduced skip connections. Skip connections existed before for a very long time. People were using them. But they were the first ones to really show that skip connections could really work better and really achieve, you know, state-of-the-art performance on this hard task. And the idea is the following. Let's say you have some input coming in. You have weights, and then you have the output. And what you do is you just add the identity function here, right? So your output is going to be whatever the nonlinearity plus the identity function. So you add a skip connection, which is just the identity, and you don't train them. You don't train the weights on the skip connections, right? So think of it this way. If I initialize these parameters to be close to 0, the output here of this f of x function is going to be fairly small. So what you're effectively doing is just taking x and copying it here. So now, if you have a 56 layers, but you have these 10 skip connections, it's effectively the model with 3 layers, right? Because you do through 3 layers, you skip 3 layers, and then you skip through 3 layers, and you skip through 3 layers, and then you get the output, right? So initially, when you initialize this model, it's a shallow model. But the nice thing about having these skip connections is that as you start training the whole algorithm, you can start adjusting these parameters. You can start adjusting what these things should be, f of x should be, right? So you can backpropagate through the model. The other trick here is that whenever you're backpropagating, the gradients will flow through here as well, right? Because it's just a copy operation. Yes, question?
So when you meant adding that, does it mean that is it just an animation of the inputs, or is it like averaging or the max?
No. This is just passing the identity. Just copy it.
Directly and then append it to what you have already.
Yeah. You're not appending it, you're just adding. Right? Think of this as states of the hidden units in layer 3. And then what you get out here is you get this output, which is nonlinearity, plus the states of the hidden units at layer 3. That's all. And so now, if you look at this model, what am I looking at here? Let's just see. Here's VGG, which is OxfordNet, 19. So you can think of it as kind of like 19 different layers. Here's 33-layer network, which is just everything is connected, you know, fully connected. And here's 33-layer residual network. So you have these skip connections that jump through multiple layers, right? And what they were able to show is that these residual networks could achieve top 5 error of about like 5%. With ensembling, you get 3.57% top 5 test error on ImageNet, which basically was hitting about human level accuracy for this data set. Yes?
So just to be clear, you can only skip layers that have like the same size, right? Because otherwise you'd have a dimensionality mismatch.
Sure. Yes. Yes. You skip the layers that have. So you have these blocks. Sometimes multiple blocks of the same size, and then you skip them. You have again multiple blocks of the same size, and you skip them. Yeah. But this one, again, it was you're now getting at the stage where you're basically becoming better than a human accuracy for recognizing these images. So at this point, people are basically saying ImageNet is pretty much solved. Like we have models that can do better than humans for recognizing all of these different thousand different classes, which is pretty remarkable. And this is done properly on the test set and everything, right? The other interesting thing I want to point out about these models, and then we'll jump to the next topic, is that when I look at these features, VGG features or ResNet features, the top layer features, right? They tend to generalize quite well to a lot of different other tasks, right? Which is why a lot of folks in the vision community, in particular, since we talk about computer vision, found these models to be quite useful. Because I can take these top layer features, or in VGG network, or in residual network, I can take these features and just use them for something else. In fact, there was a paper, I think, that took VGG features, or GoogleNet features, and just started doing classification of mammograms, medical imaging, like detecting breast cancer, for example. And they work quite well, right? Which is surprising. You're training your model on like mushrooms and hammers. You get some features and you're applying it to medical imaging domain, and it works fairly well. Tells you something about generalizability of these learned features. Or you can take these features, for example, and use them in caption models, caption generation models. Right? One interesting thing about these features is that the ImageNet dataset was specifically not, the human wasn't specifically included in as one of the classes. Right? If you look at the 1,000 classes, a human is not one of the 1,000 classes. And the reason for that was initially by design, because 40% of images contain a human. Just because when people take pictures, there is always somebody, like some human somewhere, a face, somebody's face, and whatnot. So they specifically said human is not going to be part of the class. So we don't want to detect humans or anything like that. We want to detect all of these classes. But if you take these features and you use them for caption generation system, where most of the time you have humans eating lunch or humans walking and talking, just the ones that I've shown you before, these models work like a charm, right? So it somehow is able to say something of the form, a human is really a combination of, maybe a hammer plus 0.1% of a hammer plus, 0.1% of a mushroom and so forth, right? So these features are very distributed, high dimensional, and capture a lot of different variability. So keep that in mind. Okay, so choosing architecture. Well, the architecture itself is task dependent, so there isn't one. Yeah, question?
The previous slide. What is the dotted line when the dimension did not match? Do not match.
This one?
Yeah, the dotted line.
Right
In the
side.
ResNet, yeah, the dotted line.
I don't know. I think that if the dimensions are not matching, you basically have to do the pooling operation or upsampling operation to sort of match the dimensions. So there are ways of dealing with that. Yes?
So after some point in training, like over there, what kind of changes do you do so that when you add a skip connection?
Yeah.
After some point in training, what do you do? You decrease the weight of the skip connection?
No. The weight is always identity. It's fixed at identity. You don't train it. Right? So you're just basically saying this is always identity, so this can change. There are some recent works that basically do the gaining or gating and so forth that can sort of like to decrease or increase the strength, but I think the original model was just the identity. It was working quite well. Yes?
So isn't this approach similar to having some hidden limits for which you initialize the weights to 0 and then you just ignore them during back propagation?
Why do you ignore them?
Because you are not changing their weights. The weights stay constant.
But you can't really ignore them because when you look at the gradient flows through them, right? So yes, you're not updating them, these connections, but the gradient does flow through them. And this is not really having some hidden units that you ignore. It really is just copying this to here. So if you look at the overall function, it's just going to be these nonlinear functions plus a whole bunch of additive functions from previous layers. So when you take the gradient with respect to this, will flow like this, but you also take the gradient with respect to this. And the gradient will just say, well, this is identity, and just push it down. Yeah. Maybe one last question, and then, yeah.
So in the training process, is the identity always there? Or
Yes.
you randomly turn it on and off?
No, you always keep it as 1.
So why just throw that layers away and just connect the...
Oh, because if this is 1, but then the model can adjust these layers, right? It can change the parameters of these layers, and so this function can change. Think of it as like, it's like a boosting where you have 1, but you're also adjusting the other piece. So this piece gets adjusted as well. So even though you're copying this, it's this plus this. It's this plus this. Okay, so choosing the architecture. The general thing is that you have convolution, perhaps with pooling, multiple layers, fully convolutional layer. Now you have these residual connections or residual blocks that you can incorporate, and you look at the papers that study these architectures. The general motivation is that the more data you have, the more layers and the more kernels, the more convolutions you want to have. So that's why some of the most successful models are these very large computationally intensive models. So you look at the number of parameters, look at the number of flops, and you need a lot of compute resources, right? So that's kind of where we are right now with these models. Optimization tricks. I think I've mentioned this before, but let me quickly go over them again. These models, when you look at residual networks, when you look at GoogleNet, VGG, all these state-of-the-art models are really just stochastic gradient descent with momentum, batch normalization, and dropout. 3 components that are used for training these models. You typically want to pick a learning rate by running a subset of the data. You can start with a large learning rate, you divide it by 2, and so forth. In fact, if I look at this particular model, you see where you see these jumps. And typically, what you see is that you see something like it jumps, and then it jumps, and then it jumps. But what happens when it jumps is at the point in time when you decrease your learning rate by 2. And it's super hard to beat this. There aren't a lot of automatic techniques that can do it for you. So people sometimes joke that, you're training your model, you go drink some coffee, you come back and say, okay, half the learning rate divided by 2. You go drink some more coffee, and then it's, running, and then again you divide it by 2, and so forth, right? So these are the state-of-the-art models. Okay, so you're using ReLUs, you initialize parameters, so each feature cross layer has similar variances. You want to avoid unison saturation. So keep that in mind. Improving generalization. Again, I've mentioned this before, but just to quickly emphasize, data augmentation. That's a key. Jittering, noise injection, flipping, rotating, scaling it. These are all things that can help you a lot. In fact, for these ImageNet competitions, a lot of data augmentation that's taking place. Flipping it, you're doing different crops at different locations, slight rotations and such. Dropout, weight decay, sparsity in the hidden units, that can help sometimes. Multitask, for example, whenever the GoogleNet was introducing its model, you can think of it as it's not really multitasking, but it was injecting tasks at different layers. After the first 5 layers, you have a task of predicting the label. After 10 layers, you have another task of predicting the labels, right? So that can help. Even though residual networks, instead of predicting the tasks, they introduce these skip connections, which is kind of a nice way to think about it. Instead of having 3 different losses predicting labels at each, every 10 layers, you have these skip connections, right? So kind of putting everything together into one objective function. But that can help. Let me just emphasize this again. I know I've mentioned this before. Gradient check. Check your gradients numerically by finite differences. Right. I think that for this homework, I know there's been a lot of questions on Piazzas, what's happening with my gradients, ReLUs are not working, and so forth. This is a very good test to check, are your gradients correct or not? Right? Just Google check grad. You'll find these finite differences methods of the code. You don't have to code it yourself. Yes?
So in our learn features, we just see static, like there's no pattern. But we know it's learned.
What do you mean static?
Like, I mean, you can't really see any pattern or structure.
I mean, generally, for the homework, you mean?
Yeah.
You should see some patterns. Like if it's completely like some random thing, it's a little bit bizarre.
I mean, there are like some patches and white.
Yeah, sure. I mean, you should start seeing little edges or little pieces, certain features that the model is discovering. But more importantly, you should also look at this particular plot, right? You have hidden units, you have samples, and you look at the activations of the hidden units, right? You want to make sure that hidden units are sparse, and there's not much correlation between different hidden units. When you're doing convolutional networks, right? Ideally, this is what you'd see in your first layer, right? You see some form of edges, or some form of low-level feature extractors that kind of look like this. If you look at the ImageNet models, like GoogleNet or VGG, the first layer will capture this kind of structure. So you're detecting this, like detecting orientations at detecting edges at different orientations. And this would be like, a bad structure, right? It's either too noisy, it doesn't really capture anything, it's like not sure, it's just detecting some garbage typically, or there's some lack of structure, which is just some random patterns. For visual domains, particularly for image recognition, for videos, or for any sort of anything that has anything that has where you're working with images of natural scenes, you should see this structure. And this would be an example of a bad training, and that can happen, right? If you look at, even for your homework, if you look at your hidden units, this is what if you see something like that, strong correlations, then the model is not really learning, right? It's just have a redundancy in the hidden features, same feature across all training examples. So you visualize parameters. Learn feature should exhibit some structure. Measure error on both the training and the validation set. That's important. So look at both errors. Test on a small subset of the data to check if the error goes to 0. So this is a very good another test, which I mentioned, I believe, last time, which is how do you test that your optimize is actually working? Take a much smaller set, take a subset of your data, train on a subset of your data, your training error should be 0. You should be able to overfit. If you can't overfit, something is wrong with your optimizer, right? So for your homework, for example, if you pick, 50 examples, and you run your model on 50 examples, your training error should be 0. If it's not 0, if it's like fluctuates back and forth, or even like increases, something is wrong with your optimizer, because you should be able to overfit, given the complexity of your model. Yes, question?
Can you explain more about the motor timing?
Yeah, I'll come back to that. Okay, so let's look at when it doesn't work. So let's say you look at your training and your training error diverges, right? Goes up. So the first thing to do is maybe your learning rate is too large. Decrease the learning rate. See what happens. Backprop is buggy, right? Which basically means you're not computing your gradients correctly. Do some form of gradient checking using finite differences. Parameter collapse. So for example, if you're minimizing the loss, but the accuracy is low, So according to your loss function, you're doing well, but your accuracy basically is really bad. It's almost random. You have to check your loss function. Is it appropriate for you for the task that you're trying to solve? Does it have degenerate solutions? Right? Sometimes you can come up with a loss function that you hit 0, but it doesn't really correlate with the task you're trying to solve. That's not the case for your homework assignment, but in general, this is something you should be aware of. Network is underperforming. So for example, you can't really hit 0 training error. It's sort of like training without any regularization, you're not really optimizing it. So maybe the model is too small. Make the network larger. Try a larger network. Visualize hidden units parameters. Try to fix optimization if that's the case. And then network is too slow. I guess here I can't really help you, but you should be using GPUs, distributed frameworks. There's a whole bunch of these modules right now. And a lot of software packages like PyTorch and TensorFlow and stuff like that. There's actually distributed network where you can say, run my network on 8 GPUs. And it automatically figures out how to run it on 8 GPUs, which is kind of nice. There's a lot of work that engineers sort of put into building these distributed frameworks. Yes? Which one? Oh, degenerate solution. So degenerate solution typically means that if you choose the wrong loss function, you can optimize this loss function, and your loss function can hit 0, some minimum value, but it doesn't really correlate to the task that you're trying to solve. Right? So there could be like a degenerate solution. There's some optimal solution that the model can find, but it doesn't really solve the problem that you're trying to solve. Yes?
Different solutions, then we generally the classification, for example, there's true measure decision, even if you have the same.
It could be. Could be. Okay, so in the last 10 minutes, 20 minutes of the class, what I'd like to do is I'd like to show you some examples of zero-shot learning, right? And show you the combination of convolutional networks and text a little bit. So remember what the zero-shot learning is. At the training time, you have data, X and Y. You have some images, you have some labels. And in the setting, both of these images and labels are coming from some underlying distribution. So you have IID draws from this distribution. Y belongs to one of C classes, right? So you're trying to do 10-way classification problem. And let's just look at this particular setting where you have additional data. What we're going to have is we're going to have a description vector Z sub C of each of the C classes in form of a text. I'll make it more precise as I show you examples of that. So you have some additional data that you have access to. Let's say it's a text data or another modality. At the test time, the setting is that you have these additional classes. You have these additional M classes that you've never seen before. Because it's a zero-shot learning, basically means that you've never seen these classes before, but you're trying to recognize what they are. Okay? Let me show you an example to test you zero-shot capabilities. Look at the description of this particular bird. So these birds have yellow underparts, blue-gray underparts, pink legs. They also have yellow eye rings and thin pointed bills. Adult males have black foreheads and black necklaces. Females, matures, have gray necklaces and so forth. That has a description of a bird. Can you tell me which one of these birds you have a description for? I think it's called Canada warbler. Any guesses? Yes? Leftmost part. You think this one? Yeah. Okay. How many of you think that this is leftmost part? Few. What about the middle one? Maybe 1, 2. How about this one? 1 or 2? You're not so good either. That's the correct one. So people are not very good either, and the reason why is because you kind of like seeing, well, black necklaces, and this kind of looks like a black necklace, right? So the question is, but many of you did solve this problem. The question is, how can you solve this problem, right? How to go from descriptions to recognition, which is a really, really hard thing to do in general, right? And we sort of have some understanding of what this thing is. So let me show you. Here's another example. I have a description, and it turns out, I think that this is actually the description of the flower, right? By looking at specific patterns, people are pretty good at recognizing what these things are. So let me show you a solution, one particular solution to this problem. Suppose you have a binary 1 versus all classifier for class C. Okay, we're not doing deep nets for now, but let's say I want to do 1 versus all classifier. Okay, so what I'm going to do is I'm going to say, here's my input. I apply WC, which is the weight for a specific class, and I get my target Y. How do I do classification? I compute this for all 10 classes, if I'm looking at 10 classes, and I pick the maximum. Right? That's the definition of 1 versus all classifier. You run 10 classifiers, you pick the one with the maximum output. So this is a weight vector for a particular class C. The question is, how can you deal with previously unseen classes using this formulation? Right? At test time, I give you a new class, WC plus 1. Where do you get this WC plus 1? Now, obviously you can't. So it's a hard problem to do. But let's say we're given some additional text feature T sub C. Right? These are Wikipedia web pages. Simple idea is instead of learning a static weight, the text feature can be used to predict the weights. So think of it as following. Given some textual features, I pass it through some nonlinear function, and that gives me the representation of the weight vector W. Right? And now, if I give you this description for a new class, I'm going to get a new representation of the W vector. Once I have this new representation for the W vector, I can now use it to make a prediction. So here, ft, this function, is a mapping between textual features to the visual features. Right? And you can use this idea to predict the output weights of a classifier, convolutional, fully connected, whatever it is that you want to do. Right? And there's been a few papers that kind of use these ideas where you have a different modality. You pass it through the network that's used to predict the parameters of another network. So there's been a few papers recently on one-shot learning, few-shot learning that kind of use the same idea, similar idea. So how does it work? Let's say you have a Wikipedia article. You construct TF-IDF features. For those of you who don't know what TF-IDF features are, think of them as bag of words. Okay? You do sort of alignment or a little bit of scaling of these features. C stands for term frequency, inverse document frequency. But nonetheless, it's just a bag of words. You could probably do something better by using recurrent networks instead. Then you pass it through the network. You get some representation, which is C by K. Now you take an image. You pass it through a convolutional network. You get some features. Right? And then you're just doing dot product. This is your feature of dimensionality K. And then these are your predictions for the C classes. You multiply them together, you get the class scores, and you can construct softmax probabilities, or you can do other kinds of loss functions like margin-based loss functions, and then you can train this model. Right? Very simple. And the idea is really comes to this notion of learning the semantic feature space, which is if I give you this particular article, you embed it into this k-dimensional space. Given an image, I want to embed it to the same k-dimensional space. Right? So both of them lie in k-dimensional space. I have another image, again, I'm embedded in k-dimensional space, and so forth. And this is embedding of the article and these other images as well. And what I'd like to do with these models is at the training time, I'd like to make sure that this article, this description of this article, its embedding lies close to these correct images. But it's far away from these incorrect images. Right? And this is sort of a general idea. This is the prediction where text predicts the W, and then you have image features, and you just take dot products. Right? The dot products is basically looking at cosine similarity. You have two vectors, and you're measuring distances between those two vectors by using cosine or using dot products. That's exactly what's happening here. You can minimize the cross-entropy loss or hinge loss, which is margin-based loss, to optimize for this. Yes?
Are the x and y axes that you use there just a representation of the feature space?
Yeah. This is just representation. So this would be in, typically 300-dimensional space or 400-dimensional space. Yes.
So the purpose is to train the network that can put those, match those articles to the...
That's right. You match those articles to those images. That's another interpretation of this model. Yeah. And so let's look at the problem setup. You have a training set of n images in the associated class labels, right? These are C distinct class labels. And at the test time, we're given n0 number of previously unseen classes, right? And these are the previously unseen classes. The goal is to predict previously unseen classes as well as do well on the previously seen classes, right? So you really want to generalize to the classes as well. And the interpretation here is that you want to be able to learn a good similarity kernel, similarity metric between images and Wikipedia articles. Right? And this is what the model can do. So there is something that's called BIRDS dataset, UCSD BIRDS dataset. You have about 6,000 images from 200 bird species. There's one Wikipedia article for each of the classes. So there's one description of each of the classes. The total number, the average number of words per article is about 400. Out of 200 classes, you have 4 classes. You define these 40 classes as unseen classes, and the remaining 160 classes is defined in seen classes. Right? So in other words, you take 40 classes out completely. You don't have images. You just have Wikipedia articles for those classes. That's all. So you're really doing training on 160 classes. So here, again, the intuition is that the model can start learning it to associate. What does it mean to have a black necklace? What does it mean to have a white stripe? What does it mean to have big and big, I guess, big, right? Or what does it mean to have certain colors and wings and so forth, right? Based on Wikipedia article description and what the visual images of these birds look like. And there is also flower data set, which contains about, again, 100 classes. And you're splitting them into 82 flower classes used for training, 20 classes used for testing, right? So again, you're splitting it very, so you have these distinct classes. And here's what you can do, there was a paper that looked at domain adaptation using VGG features and so forth. It's interesting that what you can see is that here you're measuring area on the ROC. 0.5 is random, 0.8 is where you get. So you can see that on the seen classes, things that you have examples of, the accuracies are quite high. These are test accuracies, right? So 0.96 and 0.98 is actually pretty high. Like you can really recognize these images. I give you a new sunflower or a new image of I give you a new image of a flower and tell you what is it. If I've seen it at the training time, you can actually get there. Here you get like 0.8 as an accuracy, which is a much lower accuracy. But I think the student who was working on this work, Jimmy, who was working on this thing, he actually tested himself. And I think his ROCs was about 0.75 or something like that. But I think that, compared to like somebody who's familiar with birds or flowers, they could probably hit these numbers, right? On flowers, it's much worse. Turns out recognizing different flowers is a much tougher thing to do, even for people. Mind you, there's like 200 different classes, right? And these are very specific different flowers. So doing a zero-shot learning is actually pretty challenging. The other thing that you can do is you can do interesting things like attribute discovery, which is I give you this entire Wikipedia page, right? And if I look at, this is a web page of Scarlett Tanager. If I go to this semantic space and I look for nearby images, this is what I'm finding, right? In addition to this, I'm actually finding these birds. So you can kind of like see that they're all kind of red, they kind of look similar, but this is not Scarlett, this is Summer Tanager, right? And like other kinds of birds. But what interestingly you can do is, so in this case, Wikipedia articles projected onto the feature space, and you look for the nearest neighbors to find out the closest images. But you can also look at the word sensitivities for the unseen classes. So what you can do is you can do the following. You can say, well, if I look at my loss, and I take the derivatives with respect to the input, with respect to the textual input, I can say which words are most influential when predicting this particular unseen class. Okay? So it turns out that for predicting scalar tanager, right, just particular class that I'm trying to predict, these words tend out to be very sensitive. So in other words, existence of this word specifies the correct prediction. If this word doesn't exist, the probability of the prediction goes down for this particular bird. So it it picks up that scalar is important, tanager is important. And if you look at these two things, this one is actually some family of this particular bird species. And this is also somewhat related to a specific feature of this particular bird. It's kind of hard. I don't even know what these words mean. But I remember we looked at them in the Wikipedia article. So we looked at the definition. So it does pick up on features on words that are specifically related to predicting this particular class. So it kind of discovers sometimes, you can think of it as attribute discovery. It's discovering which words are most important for predicting this particular class. Same thing goes for, this particular flowers, bird iris. These are the closest flowers. And it interestingly finds iris, but it also interestingly finds freezing, because these flowers tend to freeze in the winter. They don't survive if you have cold conditions. So it picks up this particular word because, it talks about that this flower can freeze in the winter. Depth compost, I guess it sort of has to do with the specific, again, nourishment of these flowers. So this is kind of was interesting to us, that in completely zero-shot learning, because you've never seen images of bearded iris before, you can find some relevant images. But not only that, you can also find the relevant attributes. You can find some attributes that would be important for defining this particular class. Yes?
Does the number of articles you refer to, does that have any impact on the word sensitivities that we find?
The number of articles? So in this case, we have only 200 classes. So we only have 200 articles. Right? So the number of articles is fixed. It's just a description of the class. Right? Of course, the more examples you have, the better your model would be. But this is, again, the idea is that you only have a description of the class. And you're trying to solve the visual recognition problem without seeing examples of this. And people are pretty good at doing that. Right? If I give you a new class and I describe you what it looks like, you should be able to recognize it. Right? Any questions? Okay, so let's stop here. So next class, we're going to start jumping into graphical models. Right? So it's probably going to be a little bit more intense compared to what we had before. So be a little bit prepared for that as well.